If you can get below the surface, you go back in time. And Victoria has this huge big hole in the ground.
You did a very long exploration of the rim.
Yeah, we spent nearly a year working our way along the rim. So what you have are these kind of alcoves, and they're just tens of meters away is a cliff.
And so you can do lots of your science.
Exactly. There's like 6 meters of vertical rock there to be imaged. But this is the tricky part. To get the shot you want, to get the image that you want, you need to drive right to the edge. So there was this incredibly intense year where you've got the rover drivers, the engineers, whose job it is first and foremost to protect the vehicle at all costs. And then you've got the scientists saying, just go a little closer to the edge. Just go a little closer to the edge, And there were times where literally we practically had the front wheels hanging over the edge of a cliff to get the shot that we wanted.
Were you always going to go inside the crater? I remember a lot of debate at the time, because what if you got stuck in there? That's it.
Yeah, we went back and forth on that for a long time. Were we going to go in and take the risk or not? The science return from going in is obviously important, because many of our instruments, you have to reach out and touch the rock.
That's right.
So you got to go down. Yeah, all the instruments on the arm, you got to go into the crater if you want to take advantage of this big hole that we're exploring. But there's the risk that you're not going to get out again. The good thing was that by the time we got to Victoria, we really had a very good handle on what we could do and what we couldn't do. We had operated it on steep slopes before. We were confident enough that we could pull it off.
And so you shuffled down slowly into the crater.
What you do is you're kind of working your way back in time geologically as you go to deeper and deeper and hence older and older layers. And we would just work our way down. And each time we got to a layer that looked different, we would take the instruments on the arm and we would use them to characterize the texture, the chemistry, the minerals that are present, and so forth. And just work our way down into the crater, doing a stratigraphic section. And the thing that was beautiful about that, geologists are big on doing stratigraphy, and a stratigraphic section is just a description of the rocks in a vertical sequence.
As you work downwards.
Exactly. And, we were incredibly proud of the fact that over at Endurance Crater, the first half year of the mission, we did the first stratigraphic section that had ever been done on another planet.
Not just picking up random rocks on the surface anymore.
Yeah, we're working our way down very methodically. But now we could do two different vertical stratigraphic sections 6 kilometers apart at Endurance and Victoria, and compare the two to look at lateral variations.
So what story did the rocks in the crater tell you?
What they told us was that the rocks there, as they were at Endurance, are sandstones. The grains of sand are made of largely sulfate salts that were formed when acid groundwater evaporated away and left these sulfates behind. Blown around by the winds, we see marvelous, some of the pictures are just fantastic. In the walls of the crater, we see the ancient remains of very ancient sand dunes that were once present, and you can see that it's called cross-bedding, where there are layers that meet at angles like this, and it's just like from a geology textbook. It's just absolutely fantastic stuff. And then, after the rocks were deposited, they interacted with liquid water below the ground, dissolving away some minerals, precipitating out others, and so forth. And the patterns are very similar to what we saw back in Endurance. So what that says is that it really was regional in scope.
So let me ask you the difficult question. Do we have any idea how far back in time this was?
I was afraid you were going to ask me that. No, I don't. I really wish I did. One of the most fundamental questions in geology is always, when did it happen? And the way geologists on Earth do that is they either look at the fossils that are present in the sedimentary rocks, which
that doesn't help
we can't do, or they do radiometric age dating by taking the rocks back to a laboratory, and that we can't do either. So I can tell you that the rocks at the bottom of the stack are older than the rocks at the top of the stack. But the absolute ages, I wish we could, but it's just a shot in the dark.
And we're not just talking yesterday, are we? We're not talking millions of years ago.
We're probably talking, billions of years ago. But if you're going to pin me down as at 1.6 or 2.2 billion, I'm going to throw up my hands.
I'll let you off this one. So how was climbing out? Did things go
as
expected?
It was tough at first. The initial parts of the ascent out of the crater, we had a lot of wheel slippage and spinning, and there were a few kind of white-knuckle days in there where we were a little nervous. But we eventually did get out of the worst of it and got back on ground where we had good traction, and out we went.
And then what?
Well, that was the interesting thing. The obvious easy thing to do is just kind of go, noodling around on the plains till the wheels fall off. Or we could try something a little more bold. And more than 10 kilometers off to the southeast, in fact closer to 20, there's this huge crater that we named Endeavour Crater. We can see the rim of Endeavour Crater on the horizon from where we are right now. We could see it a year ago.
And because it's huge.
It's huge. It's absolutely huge. The rim is hundreds of meters tall. 25 kilometers in diameter, hundreds of meters deep. It's not even a crater that was formed in the layered sedimentary rocks. It's an ancient crater, huge thing that predates those sediments, and the sediments were deposited over top of it, and then there's bits of the rim sticking up through the crater. So it's really, really different. And we decided we got to pick some direction to drive. Let's go for that thing. We were talking about more than doubling the total mileage on a 5-year-old vehicle that was designed to last for 90 days and go a kilometer. So let's just say that the odds were not in our favor, okay? But it has just energized the science team, the engineering team. Opportunity is just a fun vehicle to operate these days.
Well, let's swap sides of Mars. Spirit?
Spirit has had a tough time. And about 800 days into our 90-day mission, the right front wheel on Spirit failed, and we have to drag it. So Spirit, which used to climb mountains and drive 100 meters in a sol on a Martian day, a really good day would now be 5 meters. And we have to drive the vehicle backwards, dragging the dead wheel through the soil, and it was painful. So one day we're driving along through this little valley, dragging our dead wheel. We get to the end of the drive, and we look down at the wheel tracks, and they're as bright as white snow. So that got our attention. We go over, we whip out our X-ray spectrometer, we measure the composition of this stuff. It's 91% pure silica, SiO2. Now, this is not quartz. This stuff is not beach sand. It's basically opal. And there's lots of it. And we never would have seen it if it hadn't been for the dead wheel. That was what exposed it. What we've come to realize is that these silica deposits are the remains of an ancient hydrothermal system. If you go to a place like Yellowstone, where the geysers are, and you look around the geysers, there are these beautiful sort of whitish, bluish rocks around them. Those are silica that have been precipitated out of the water. And you can go to hot springs on Earth, and they're teeming with microbial life. So this was the remains of an ancient hydrothermal system, an ancient habitable environment on Mars. And we found it because of the dead wheel.
So where's Spirit now?
Spirit's stuck. So unless some absolute miracle occurs, Spirit has found its final resting place on Mars. And we transition from being a rover mission into being a lander mission.
It must hurt to have the rover stuck.
I think the day when it suddenly hits us, we've gotten our last transmission from the vehicle. That's going to be, I think, pretty hard. There have been 1 or 2 times over the course of the mission where, major dust storms particularly, where it looked like the power system was just getting so ragged that we were going to lose the vehicle. And so the most likely way in which a stationary vehicle dies is too much dust on the solar arrays, seasons change, and we lose power. We can't keep the thing alive. And I don't anticipate that's going to be a good day. It's had a good life, a good, long, productive life, and it's achieved so much more than any of us could ever have anticipated or hoped for, that if this is the end, it is clearly an honorable death.
Before Spirit can start its new life as a stationary laboratory, it has to survive the harsh Martian winter, which is likely to send the rover to sleep for weeks or even for months. On the other side of the planet, opportunity is still going strong. It's only just visible amongst the sand dunes on this image, captured from space by the Mars Reconnaissance Orbiter. It'll be a long, hard slog, but 7 miles and thousands of sand dunes away lies her target, Endeavour Crater. Let's hope she makes it.
Well, who knows? In the foreseeable future, astronauts may go there and find Spirit and Opportunity, and they'll wait for us. then nowhere else to go.
That's very true. And for the amateur in the meantime, there's plenty to do. If you're a visual observer, there's plenty of work to be recording on Mars, and the imaging.
If you've got a telescope with a camera, then go out and grab it now, because it's at its best.
So go out, find Mars, use what equipment you have, and make the most of this opportunity, because it will be some time before Mars is again really well placed. Paul, Pete, thank you very much.
Pleasure.
Thank you.
Next month, a special program